So by now we've defined this idea of having n elements, where a set A has n elements if and only if and only if there exists a bijection between A and n, right? And n is a natural number. So this part says there exists f mapping A to n, which is a bijection. So we've defined this idea, having n elements, or having cardinality equal to the cardinality of n. So here's an immediate nice thing that you have. 5, for example, has 5 elements. Again, this is not something that had to happen. It just happened to happen in our particular way of constructing the natural numbers, and we take advantage of it. So in our framework, 5 actually does have 5 elements. And if you stare at the elements of 5, then you can see that there are 5 of them. So that's one one perspective you can take here. But that's not what this means. It doesn't mean, oh, if you stare at it, then there are 5 of them, right? It means there exists a bijection. So why does 5 really have 5 elements? Not because I'm pointing and counting here, but because, in fact, 5 is a natural number, and 5 wiggly equals 5. What does 5 wiggly equals 5 mean? It means there exists a bijection from 5 to 5, which, there exists a bijective function from 5 to 5. And how do I know there exists one? Well, I can use the identity function. So this is a special case of our earlier result, theorem 115.1, that everything wiggly equals itself, because you can use the identity function as your bijection. So great, 5 in fact does have 5 elements. So that's actually a pretty easy thing to establish. But how about this question? Does 5 also have 4 elements? I mean, it sounds ridiculous. If a set has 5 elements, how could it also have 4 elements? But the way we defined has n elements doesn't immediately preclude the possibility that something could have 5 elements and then also it could have 4 elements. So we'd like to say no. Hopefully 5 does not have 4 elements. If it did, then probably something is wrong with our definitions. So hopefully the answer is no. But how would we prove something like that? How can we know for sure that 5 does not have 4 elements? Well, we'd have to prove that there does not exist a bijection between the natural number 5 and the natural number 4, right? So you have to prove not there exists a bijection between 5 and 4. Or if you push the negation through that statement, you have to prove that for all possible functions from 5 to 4, they are not bijections. All the functions 5 to 4 are not bijections. So one way to try to prove that would be to go through all of the functions from 5 to 4. There are a lot of them. That is a lot of functions to go through. All of the different ways of mapping the elements of 5 to the elements of 4. And then for each one in a giant proof by cases, for each one of those just verify that one's not a bijection, that one's not a bijection, that one's not a bijection. And even after you do all of that work, you would only have resolved one question, the question of whether 5 has 4 elements. What about the general question? Does n have m elements? We'd like to say that the answer is yes, if and only if n equals m. So that if n does not equal m, then the answer is no. We'd like to answer this question in general with a proof. So even the terrible idea of doing a giant proof by cases would not work to give you a general proof in a context where n and m are natural numbers. And that's where theorems 122 and 123 come in. So actually the theorem that directly answers the question that I just posed is theorem 123. N has m elements if and only if n equals m. So that's we should be really glad that that's true. If it weren't, then we should be worried that our definitions are wrong. So very good. But theorem 122 is actually where all the hard work will be. And theorem 122 will be used to prove theorem 123. So theorem 122 says that if there exists an injection from n to m, then n must be less than or equal to m. And conversely, if n is less than or equal to m, then there exists an injection from n to m. So I just want to convince you that if we have theorem 122, then we can prove theorem 123. So let's suppose we have theorem 122. For natural numbers n and m, an injection from n to m can exist if and only if n is less than or equal to m. Then I claim we can prove theorem 123, which starts by assuming you have two natural numbers, and then it also makes a bidirectional claim. First, assume that n has m elements, or n has the same cardinality as m, and then we will prove that n equals m. And in the other direction, assume n equals m. This one is easy. This direction is easy. Doesn't need any work, really. So if n equals m, of course n has the same cardinality as m because n has the same cardinality as itself. And we just mentioned this property reflexivity for this relation. So maybe I can write this a little bit better. Then since n has the same cardinality as itself, by that earlier result I just showed you, reflexivity, we have this sort of using axiom 2, right? Replacing something by something that it's equal to. Okay, so that direction is pretty easy. But then this direction is going to need the hard work from theorem 122 to prove this direction. So assume n has the same cardinality as m. Well, then there exists a bijection from n to m, right? So it follows that there exists an injection from n to m, since bijections are injections. So then, so let me skip a little bit. So this is not my main focus. My main focus is I want to prove theorem 122 today. But I just want to show you that you can get this. So if the step from here to here is, if there's a bijection from n to m, which is what we're assuming here, then there's an injection, since bijections are injections. We also have m has the same cardinality as n. That relation is symmetric, right? Symmetry for this. If you have it one way, you have it the other way. So also, there's an injection from m to n. So now we know that there exists an injection n to m, and there exists an injection m to n, right? They might be different functions. They probably will be different functions, but they exist. So by theorem 122, n is less than or equal to m, and m is less than or equal to n. So n equals n. Where am I getting that? It is a consequence of the trichotomy law for the ordering on the natural numbers, and I think I put it into an exercise here, exercise 119. If you have inequalities like this going both ways, then you have equality. So this is called antisymmetry. So using the result from that exercise, from exercise 119, from n less than or equal to m and m less than or equal to n, we get n equals m. So that's it for proving theorem 123 using theorem 122. And so if we can prove theorem 122 that the curvy less than or equal to symbol holds if and only if the solid one holds 4 natural numbers. If we can prove this theorem, then we will have a solid answer to these kinds of questions. Does 5 have 4 elements? Theorem 123 says 5 has 4 elements if and only if 5 equals 4. And does 5 equal 4? No, because 4 is less than 5. And the trichotomy law says that things can, it says that you have trichotomy, so you can't be less than something and equal to it at the same time. So theorem 123 definitively answers these questions. Okay, you can imagine that if you're working with finite sets and you want to prove theorems about finite sets, then it will be important to have simple questions like this completely down and have tools for working with those. So I hope I've convinced you that it is valuable to be able to prove theorem 122. And let's spend the rest of this lecture proving it. This is going to be, I think, one of the most fun theorems that we do in the course, and probably one of the most complicated that I've chosen to include in the lectures.